And now we're going to do a couple examples of building confidence intervals. I have 3 examples on this page, but I think maybe we'll do 2. And if I remember, I can put one on the final, which I just sent you an email about, and I'll be interested what you think about my idea. Here is a situation, an automobile company putting in a new fuel injection system to improve gas mileage. Let me see. I want to see if it did improve gas mileage, so I take a random sample of 15 test runs, and here's the miles per gallon obtained by the 15 cars. Okay, random sample. Okay, I want to build a 90% confidence interval that will contain the true mean gas mileage mu. And again, 90%er, here's my sample data. I might capture mu, I might not. We hope I do. 90% of the time I will. So I put all this data into Minitab in a column, and I asked Minitab to give me descriptive statistics so I wouldn't have to work on it now and do all these calculations. So here is sample size. This is X bar for the sample of 15. This is the median. So if you list them high to low, middle value. Trimmed mean just means you list from high to low and you trim off. It's kind of like the Olympics, right? You take a few low, you take a few high, you get rid of them, and then you average what you're left with. It's a good example. If you've been watching gymnastics, they do that, swimming, diving. This is the standard deviation for the sample, but we were told that the population standard deviation is 2.4. Population means you know what it is for entire population. I realize that's a little bit hard to tell. I mean, if you don't know mu, how do you know sigma? But if by chance you do have it, this overrides S. This is S. This is the standard deviation for the sample. This is the standard deviation for the entire population. This, of course, is more accurate than an S would be. It's just an estimate. And standard error of the mean is just your standard deviation, in this case your S, divided by your square root of 15. So anyway, what do I want to do here? 90% confidence interval. Assume mileage is normally distributed. And the reason why I'm doing this is I have a small sample size at 15. If your mileage wasn't already normally distributed, I really can't call the central limit theorem into play with 15. I mean, probably at 15 you would be okay, but technically, if you started with normal, you know you're normal. But in general, if I didn't have this sentence in, this would be a little bit maybe not too truthful to build this confidence interval. So that's why I need the assumption of normality, because I can't call in the central limit theorem. So our confidence interval is the mean 40.667 plus or minus. I'm building a 90%, and eventually maybe these numbers will start. I don't know. I don't want to say you want to think about them in your sleep, but you kind of start to. So this is for 90%, 2.4 divided by square root of 15. Lower would, minus, you get the lower end, add, you get the upper end. So there's my confidence interval, and even when I build it, I don't know if it contains mu or not. I mean, that's the chance that we're taking. You get a random sample and you hope it's representative and that you'll capture mu. So, I don't know. Let's just go with, I guess I'll skip this one right now. I'll go down here. The fill weight of Gatorade drink bottles is collected for 100 bottles. Fill weight, okay. The sample mean is 15.97, so X bar is 15.9 ounces for N equals 100. So you took 100 bottles to get that 15.9 with a standard deviation of 1 ounce. And I guess that's sample mean is with a, it's not clear on this if this is sigma or S, but we don't have any other data, so we have to use this as our sigma anyway. So sigma equals 1. Determine a 90% confidence interval for the true population fill weight. I mean, let's change that because we've done so many 90s. Let's make it, 86% confidence interval. So what is 86? That's 24, 14. So we want 7% in each tail, right? If this is an 86% interval, I want to figure out what 0.07, 0.07. So let's go to our Z table. 0.07. This is it's kind of in here, right? I mean, not perfect. It'll be 1.48. 1.48. That's good. So this is negative 1.48 and 1.48. So our 86% confidence interval is 15.9 plus or minus 1.48 times sigma divided by square root of 100. And notice I didn't care what the fill weights were, if they were normal or not, because I have a sample of 100, so I know that the graph of x bar will certainly be a bell curve. So I think I'll leave 8 there if you want to compare answers or check, or maybe I'll just save 8 for the exam. Wouldn't it be nice if we can color? Well, it is kind of cool. I can color with this pen, but I'm sure I should just end this video now. But it's kind of cool, huh? Give this guy a little bit of red hair or something. I don't know. Anyway, okay. Nice little lips there. Okay. Anyway, so I think I'll do maybe one more or two to show you how to go backwards and compute sample size needed for a confidence interval.